In 1935, three physicists, Albert Einstein, Boris Podolsky, and Nathan Rosen, published a paper that was less a discovery and more a declaration of war against a new and unsettling vision of reality. Their paper, titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" wasn't aimed at a fringe theory. It was a direct assault on the foundations of quantum mechanics, a field Einstein himself had helped create. At its heart was a phenomenon so bizarre, so contrary to every intuition about space, time, and causality, that Einstein would later mock it in a letter to his colleague Max Born as spooky action at a distance. This spooky action describes a connection, an instantaneous link between two particles that could be separated by the width of a laboratory bench or by the gulf of interstellar space. If you were to measure a property of one particle, its distant twin would instantly adopt a corresponding state. Instantly. Not at the speed of light, but faster, in a way that suggests the distance between them is a cosmic illusion. This single observation threatened to shatter the bedrock of physics, the principle of locality, the common sense idea that an object can only be influenced by its immediate surroundings. To grasp the depth of this rebellion against classical physics, consider the setup. Quantum mechanics predicts that we can create a pair of particles, say two photons, from a single event, like an atom transitioning to a lower energy state. We can arrange it so that their properties are linked, or, for instance, their polarizations must be opposite. If one photon is measured to have a vertical polarization, the other must instantly be horizontal. The quantum riddle is this. Before you measure it, neither photon has a definite polarization. They exist in a ghostly haze of all possibilities at once, a state called quantum superposition. It is the act of measurement itself that forces one particle to choose a state. And at that exact moment, its entangled partner, no matter how far away, makes the opposite choice. This is where Einstein and his colleagues drew the line. For them, this was absurd. It implied that information, the result of the first measurement, was traveling faster than light, violating the cosmic speed limit that underpins his theory of relativity. Einstein, a champion of realism, proposed a far more sensible alternative. The particles, he argued, were not in a state of fuzzy potential. They were like a pair of gloves, separated at the factory and placed into two identical boxes. One glove is for the left hand, one is for the right. You don't know which is which until you open a box, but the glove-handedness was determined from the very beginning. If you ship one box to the moon and open the other on Earth, you will instantly know which glove is in the lunar box. There's nothing spooky about it. The information was always there, hidden within the system. These predetermined properties were what physicists came to call local hidden variables. The quantum description, according to the EPR paper, was simply incomplete because it failed to account for these hidden instructions. The universe wasn't playing dice, we just couldn't see all the rules of the game. For decades, this debate remained a philosophical stalemate. Was the universe locally real, as Einstein insisted, with hidden rules we had yet to uncover? Or was it fundamentally non-local, bound by these strange, instantaneous connections that defied our understanding of space? The question cut to the very nature of existence. If a particle on the far side of the galaxy can be linked to one in your hand, what does distance truly mean? What unseen architecture connects the cosmos? Are these particles whispering to each other through a secret network, a ghostly cosmic network, bypassing the very fabric of space-time we inhabit? That question, once a battle of theoretical titans fought on chalkboards, has now been settled in the cold, hard reality of the laboratory. The verdict is in, and it is resoundingly in favor of the spooky. The universe is not locally real. Following the EPR paper, the debate languished for nearly 30 years until, in 1964, a physicist at CERN named John Stuart Bell devised an ingenious theoretical test. Bell was not trying to prove quantum mechanics right. He was trying to give Einstein's hidden variables a fair chance. He formulated a mathematical theorem, now known as Bell's inequality, which essentially states, if the universe is governed by local hidden variables, then the statistical correlations between measurements on two separated particles can never exceed a certain value. However, if quantum mechanics and its spooky entanglement were correct, that value would be violated. Bell had turned a philosophical argument into a testable hypothesis. He had drawn a line in the sand, and all that was left was for experimentalists to perform the measurement and see which side of the line reality fell on. The first crucial tests came in the 1970s, but it was a series of experiments in 1982 by a team led by French physicist Alain Aspect that provided the most compelling evidence. Aspect's setup was a masterpiece of precision. He generated pairs of entangled photons and sent them in opposite directions to two detectors. Crucially, he used ultra-fast switches to change the angle of the polarization detectors. This closed a critical loophole. The detector settings were changed so quickly that no signal, even one traveling at the speed of light, could pass from one detector to the other to coordinate their results. The particles couldn't have agreed on their hidden instructions beforehand. The results were unambiguous. Bell's inequality was violated, just as quantum mechanics predicted. Einstein's classical intuition was wrong. Since then, dozens of ever more sophisticated experiments have confirmed Aspect's findings, closing every conceivable loophole. In 2017, a Chinese satellite named Mischius performed an entanglement experiment with two ground stations separated by over 1,200 kilometers, beaming down entangled photons from orbit. Satellite quantum entanglement, spooky action, is not a lab-scale quirk. It is a fundamental, planet-spanning, and likely universal property of reality. But if this connection isn't a signal traveling through space, what is it? From that paradox emerges a radical, mind-altering theory from the frontiers of physics, the ER-EPR conjecture. Proposed in 2013 by Leonard Susskind and Juan Maldacena, it suggests a profound identity. Einstein-Rosen bridges are equivalent to Einstein-Podolsky-Rosen pairs. An EPR pair is just another name for two entangled particles. An Einstein-Rosen bridge is the technical name for a wormhole, a theoretical tunnel through spacetime. The conjecture, born from explorations into quantum gravity and string theory, proposes that two entangled particles are, in a very real sense, connected by a microscopic wormhole. This isn't a traversable wormhole from science fiction. You can't send a message through it. In fact, trying to do so would destroy the fragile connection. This neatly preserves causality and upholds the no-communication theorem, which states you can't use entanglement for faster-than-light communication. The spooky action isn't information traveling spacetime. It's a consequence of two particles being connected of it through a geometric shortcut. In this view, spacetime itself is not fundamental. It's an emergent property stitched together from a deeper layer of quantum entanglement. The vast network of these microscopic wormholes, this ghost network, the fabric of reality. Every particle, then, is not just a point in space, but a potential node, a gateway in an invisible, instantaneous cosmic web. The universe isn't a collection of separate things happening in a pre-existing container of space. It is a single holistic quantum object, a symphony of unseen, instantaneous connections humming across the void.